So there you are working on your Python code. All of a sudden you hit with this bad boy, name error, name X is not defined. Or something like this, unbound local error cannot access local variable count. You're not even sure what this means. To know what it means, you need to master Python scope. Wait, don't leave. Yes, I know scope is boring, but Yoda always said, doing the boring stuff makes you stronger. Maybe that was Ted Lasso. Anyway, today we're looking at how Python finds names, the names of functions, variables, and classes. And when we're done, you'll know exactly what to do when you see an error like this. Let's begin. Every variable in Python has a home, a place where it lives. This is called scope. The scope of a variable is just that area of code where the variable is accessible or visible. Let me show you what I mean. Here's a simple function called f1. f1 just defines a variable x, sets it equal to hello, and then prints it back out. If we were to call that function, we get the expected hello back in the terminal. Now in this case, x is available in local scope. It's defined within the body of a function, and it's accessible and visible within that body of the function. Later on, if we try to call the variable x, we'll see that we have a name error because x does not exist anymore. X is only available within the function body, and after the function runs, x ceases to exist. Let's look at another example. Here we have function f2. We're still printing a variable x, but instead of defining x within the function body, we're defining x at the top of the module. There's no indentation, you don't see the x appearing within the function body. If we define x as hola and the function f2 and later on call f2, we get the expected string back in our terminal. Even though x is not defined in the function of the body, Python is able to reach into the top of the module to something called global scope to print the value of x. And we can have x's appearing in both local scope and global scope. In this third example, we have function f3. Function f3 defines x as hello and then prints it, but we also have a value of x at the global scope called hola. Let's see what happens if we run this. In this situation, f3 runs and we get the output of hello, meaning that when we were trying to print x, Python found this x of hello and printed that, and it ignored x equals hola. So in general, if you have a local variable as well as a global variable, within the function, Python will prefer to use the local variable. You can kind of see that Python has some kind of search process when figuring out which variable to use. And you might be wondering, well, what happens if we have more than one or two instances of x like we saw here? Let's talk about it. This is a picture that my kid drew, and we're going to use that to understand scope. Python's a lot like a kid, looking for his favorite toy. If he can't find the toy in the bedroom, he then looks in the rest of the house. And if the kid can't find the toy in the rest of the house, it moves on to continue the search outside. In the same way, when Python is looking for a name, like the name of a variable, it starts by looking in something called local scope. And if the name can't be found there, it moves on to enclosing scope. If the name's not there, it continues to something called global scope, and if the name's not there, we go on to built-in scope. After all four of these scopes, if the name still cannot be found, we get that name error that we saw earlier. These are the four scopes in Python: local, enclosing, global, and built-in. And the process of iterating through these four scopes is called the LEGB rule, the first letter for each of the names of the scopes. We've seen local and global scope already. Let's briefly talk about built-in scope. Built-in scope has those objects that you work with every day. They're the objects that come built in with Python. Let's look at them. A quick way to look at the objects available in built-in is to look at the Dunder built-ins dictionary. I'll just print the keys here. And in the terminal, we can see the objects that are available. We see some common functions like len or eval, as well as the exceptions and errors that you commonly see when you're running a Python program. Knowing that built-in scope exists and that it's the last one to be searched, we want to be careful when we name things. We don't want to give our variables a name of something that's in the built-in scope because we're effectively masking it. Let me show you with an example. You may be familiar with the absolute value function in the built-in scope. It's abbreviated as AVS, and we can see that it exists currently in the built-in scope. The absolute value function does what you learned in math class. It takes whatever number you put into it and returns a positive version of that. Here, the absolute value of -4 gives us the expected value of +4. Let's suppose that somewhere in our code, we define our own function with the exact same name. That's what we're doing here. Now, if we wanted to look at the absolute value function, we see that we're not looking at the built-in scope version. We have our own function that's in global scope. Not a big deal, but suppose that elsewhere in your app, you do want to use the original absolute value function, and you have somewhere the absolute value of -4, you're expecting to get a 4, but you get this instead. The reason you get this is because you've defined a global absolute value that takes precedence over the built-in absolute value. We can fix that though. We can fix our reference to absolute value by deleting it. And now when we look at absolute value, we have access again to the built-in scope, meaning that if we got the absolute value of -4, we get +4 as a response. So again, be careful how you name things. Okay, we've seen local scope, global scope, and built-in scope. Let's circle back and now look at enclosing scope. Enclosing scope commonly appears when you have nested functions or functions within a function. It's kind of an advanced topic, but we'll build up to it slowly. Here we have a function called function1, and within that function, we're defining another function called function2 that does something like print a variable x. After defining function2, the body of function1 calls function2. Let's suppose that within this, we have several different values of x in the global scope, in the local scope, and something in between. And after we've defined our function1, we actually call it. Maybe you already know what's going to happen for this function. Specifically, when we call function1, what will be the output of our print statement? Will it be 0, 100, or 200? Let's see. Here's our function. When we run it, the output is 200, and that's probably not surprising. We know already that when looking for the name, Python starts the search in local scope. Here in our print statement, the local scope already has a value of x, and that's what gets returned. But what if this x wasn't here, and this x wasn't here either? In that case, running the function gives you 0, because Python goes all the way to global scope and finally finds a value of x there and prints that instead. What if we did have x equals 100 here though? Then instead of going to global scope and getting 0, we get x equals 100. This x is within the enclosing scope. Relative to the inner function of function2, x equals 200 is in local scope, x equals 0 is in global scope, and x equals 100 is in the scope of the outer function. And that's all enclosing scope is. Relative to the inner function, enclosing scope is whatever is available to the body of the outer function. Cool. Just kidding. This isn't cool. This is a fairly boring and pedantic example. Let's look at something a little more interesting. We have another set of nested functions here. The outer function is called getCollector, and it does 3 things. It defines a variable series as an empty list, it defines a function called store, and then returns that function store. The inner function store does 2 things. It takes some name series and calls the append method, and then it returns the length of series. Now, if we look at this as a whole, you know that series is not defined in the inner function of store. So using the LEGB rule, Python will find series in the enclosing scope. Let's run it and see what happens. We'll call getCollector, then we can call collector, which is really calling the instance of store with different inputs of x. Here I'm calling collector with 3 different values, Harry, Ron, and Hermione, and each time I get the number of values that are in that series object, 1, 2, and 3. That means that the store function that is returned is somehow able to access the series that was available in the outer function. And that's a pretty big deal because we just talked about how after a function runs, the variables defined within that function cease to exist. Yet, even after a getCollector is run the first time on this line, the variable series still exists. This is a really cool scenario. It's called a closure. Here, our inner function store is acting as a closure, meaning that after the outer function runs, that inner function store that's returned still has access to its enclosing scope. That is, store still has access to series. A closure is basically an inner function that's returned and packaged up with the stuff around it. So for closures, we have 2 kinds of variables, local variables and free variables. Local variables are those variables that are defined within the function, like x as a parameter, and free variables are those that are defined not in the local scope or the global scope, but in the enclosing scope relative to that inner function. And we can inspect this. If we look at our collector object, there's this dunder code attribute that lets us see how the code is organized within the function. We can call the co-free variables and see that we have access to the free variable series. We can also see the local variables in co-var names, and we get that x as the function parameter. If we want to see the content of that series list, we can call the dunder_closure attribute and dig around until we get those contents. Here we can see the 3 items that we loaded into our collector object. Cool. Closures let us retain state or keep track of certain pieces of information. This closure called collector has its own series list. We can create another collector and notice that it has its own series list. Let's make collector 2. And we'll load up collector 2 with a few other objects. And if we compare both of these, you'll notice that the first collector has its own objects and the second collector has completely separate objects. This is great. It's like we have different instances of a class. Speaking of classes, this whole logic could be handled with a class where we have an init function that initializes our series as a list and then a store method that takes the input x and appends it to series. But for this simple context, classes are overkill, and closures can be a really simple functional approach to retaining state. All right, so far we've seen how we can access variables outside of local scope, whether it's an enclosing scope, global scope, or built-in scope. But we've only talked about reading variables outside of local scope. What if we want to modify those variables? Let's try it out. Here's a global variable called counter, and we're initializing it to 0. We also have a function called update counter that takes that value and adds 1 to it and stores it back to counter. When we define the function update counter, the interpreter has no problems with it. But when we execute that function update counter, we get UnboundLocalError. This is that confusing message that's hard to understand. But let's break it down. Here we can see the error message. It says cannot access local variable counter where it's not associated with a value. To understand this error, we need to know 2 different kinds of times in Python, parse time and runtime. During parse time, Python is just interpreting the file that you give it or the code that you give it to understand what it is that you want to do. But at runtime, it's actually executing that code. When parsing the definition of this function, Python sees that you're defining a variable counter and it says, oh, I'm going to make this a local variable when I compile it into bytecode, because you're saying that you're defining a variable counter right there. Later, during runtime, Python comes back to the compiled code and sees that on the right-hand side of the equal sign, we need the variable counter and we need to add 1 to it. In the bytecode, counter is saved as a local variable, so it looks in the local scope for a value for counter, only to find counter does not exist. And that's what this error message is saying. It says cannot access a local variable counter when it doesn't have a value. Because counter is defined as a local variable within the compiled bytecode, the interpreter doesn't continue the search after failing to find something in local scope. It doesn't go on to enclosing scope and beyond. But we can change that. All we need to do is add 1 line to our function. In our function update counter, we can give a global keyword to tell Python, hey, whenever you see counter within the body of this function, I'm talking about counter in the global scope, not counter in local scope. Let's run this. We'll reinitialize our counter just to be safe and then define our new function with that global keyword. And if we run update counter, no error message, no UnboundLocalError message. We can run that as many times as we want and then see that the value of counter is 3. Now, if you're curious about how your function is being compiled into bytecode, you can use a module called the disassembly module. Here I'm importing the disassembly module and I'm calling the disassembly function within disassembly module on our update counter function. Here we see a stack of the bytecode, or how the interpreter is compiling that function. This is for the latest version of update counter that used that global keyword. Let's skim through this stack, or the operations that are being performed. We're first loading counter from the global scope. We're loading a integer 1 as a constant, and then we're performing a binary operation, adding the 2 together, and storing that back into the global variable of counter and returning nothing. So when we use that global keyword, the bytecode will interpret counter as something that has to come from the global scope. Let's go back and redefine our earlier function that did not have the keyword. And then we'll call our disassembly function again, but this time when load encounter, we're using something called load fast check, which is a way of saying, hey, just pull this from the local scope. The disassembly module is new to me. If you have any other use cases, please let me know. I think it's pretty cool. As amazing as the global keyword is, don't use it. It's bad practice to modify global variables from within a function. And rather than lecturing you like your mom, I'm just going to give you an example so you can feel the pain yourself. Here we have a global variable called tax rate, and it's stored as 7%. By the way, when you have a global variable, it's conventional to make the variable name uppercase. We also have a function called calculate total that takes some input of price and applies the tax rate to it to get the total price. For example, if we call calculate total with a base price of 100, we get the expected $107. Suppose that somewhere else in your application, you have a function that dares to modify this global variable. Here we see the global keyword, and this function set tax rate is overriding that global tax rate with whatever the input is. Suppose that someone in the government calls this function and changes 7% to 50% for the tax rate. Elsewhere in your code, you might still be running calculate total and expecting to get $107, and you realize you now have $150 for your total price. When you start debugging, you go to the source code and see what's going on. And you look at the definition of calculate total, notice that we need the global variable tax rate. You look at the tax rate and you see that it's still 7%. In the actual source code, the tax rate is still 7%, but somewhere else in your application, there's a function that's dynamically changing that to be 50%. This kind of bug is very difficult to catch. So for that reason, don't change global variables. In this simple example, we can see exactly what's happening, but in a real project, your code might be separated among multiple files with thousands of lines of code, and finding a bug like this is very hard to do. Just as we can modify the global variable, we can also modify variables in enclosing scope. Here we have a pair of nested functions. The outer function defines a variable count of 0, and the inner function tries to add 1 to that variable count. We'll call the outer function, which gives us access to that inner function. And if we run that function, we get that unbound local error again. Here, just as before, when Python is parsing the file, it recognizes that you are defining a variable count in this inner function. So in the bytecode, it says, okay, count is a local variable. And when running the function, Python sees count on the right-hand side, tries to access count in the local scope only to find it's not there, and then it gives up. Just as before, we can change this by adding a keyword of non-local instead of global. Then when Python parses this file, it sees non-local count, which effectively tells Python, hey, when you see count in this inner function, do not look in the local scope, look in the enclosing scope or one scope out. This is the only change that we need to make. And if we redefine the function and call it, we can call that inner function a few times or as many times as we want. The function runs without any problem and we can see the value of that count within the closure. Let's summarize. We saw that we can't modify objects in enclosing scope or global scope unless you have certain keywords. If you want to change something in enclosing scope, you need to have that non-local statement. And if you want to change an object in global scope, you need to use the global keyword. We learned a lot today. We learned that scope is just the area of code where a variable is visible or accessible. Our discussion focused on variables, but the same rules apply to the names of functions and the names of classes. Python has 4 scopes: local, enclosing, global, and built-in. And when looking for the value of a name, Python follows each of these scopes progressively following the LEGB rule. Remember this, and the next time you see a name error or a unbound local error, you'll know what to do. Is there something else about Python that you find confusing or hard to understand? Let me know in the comments below. And if you like what you see, please like and subscribe. Until next time, happy coding.